Hi folks, welcome to 11.1, and in this video we're going to talk about sequences and their notations. So we're going to go ahead and get started with some key definitions. So a sequence is a function, all right? A sequence is a function that has a domain of only positive integers, all right? And so that's going to be really important for us because we're looking for numbers now that are only integers, all right? And in particular, they have to be positive. So all of these domain, they have to be greater than 0 and only whole numbers, okay? Now, the numbers in a sequence, we call them terms, all right? And the way we notate sequences is we use A with a little subscript, so a little number down below. So A sub 1 is the first term. A sub 2 is the second term. A sub 3 is the third term. And then we could say A sub n is some random term. So then the one that comes before it is A sub n minus 1. And the one that comes after it is A sub n plus 1. Now, we can write two types of formulas for these sequences, and that's going to be something that we take a look at throughout this lesson. We're going to be looking at something called recursive equations, and we're going to be looking at something called explicit equations. All right, so keep your ears out for both types, a recursive and an explicit. All right, before we move on to examples, I want to talk very briefly about two different types of sequences. So not the different formulas, but the different types. So we have two main types of sequences. The first one is a finite sequence. And in a finite sequence, we have a limited number of terms. Okay, so there's only a set number of terms we have in this sequence. In contrast, an infinite sequence, there is no end to the sequence, okay? In fact, the sequence keeps going on forever and ever and ever. So we don't ever reach the end. It just kind of keeps going, all right? So we've got a few vocabulary terms again here, what a sequence is, what a term is, how we annotate it, and writing two different types of formulas, the recursive and the explicit, okay? So let's go ahead and get started with an example. Example 1. Consider the sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, and it keeps going, okay? So this, my friends, would be an example of an infinite sequence. And the way we list the numbers, we list them in between, but we use these squiggly brackets to denote the numbers inside of there, okay? So because we have the dot, 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 we know that we have an infinite sequence. It goes on forever and ever. And our task here is to write a recursive formula for our sequence, as well as an explicit formula for our sequence. Okay, so we're going to jump right into seeing what a recursive and an explicit formula mean. So we're actually going to start with the recursive one. And usually when we have a list of numbers, that can be one of the easier ways to define a sequence, okay? So I usually like to start by listing out the term. So I know that A sub 1 is the number in the first spot. So that is 0, okay? That means 1 here is A sub 2. It's the second number in the sequence, okay? Now, according to our list, we know that a sub 3 is 1. However, I want us to notice something else. Maybe you already know this sequence. 0 and 1. If I take 0 and I add it to 1, I get 1. Okay, so instead of writing a sub 3 at first, I'm just going to write a sub 3 equals a sub 1 plus a sub 2, which is 0 plus 1, which gives us 1. Okay. Now, I wonder if that pattern continues to work, meaning does a sub 4 equal a sub 2 plus a sub 3? Well, I don't know. Let's find out. So a sub 4 is 2. 1 plus 1 gives me 2. 1 plus 1 gives me 2. And let's do a few more for good measure. Does a sub 5 equal a sub 3 plus a sub 4? Meaning, does the 1, 2, 3, 4, does the fifth term equal the previous two terms added together? Well, 1 plus 2, that definitely gives us 3. So 1 plus 2 gives us 3. So what we have here is actually the start to our pattern. And the pattern here is really what helps us write the recursive formula, okay? It turns out that for any a sub n, all right, we take the term that is 2 before it, okay? So a sub 5, I'm going to take a sub 3, that's 2 terms before it, plus the term that is just 1 term before it. So we would write that a sub n minus 1. So the n minus 1 means 1 before, and the n minus 2 means 2 before, okay? Now we are almost at our recursive equation. There's a few things that I want us to be really specific about, okay? For our recursive equation, we need to define our starting term. And in this case, we actually need to define 2 starting terms, like the first 2. So a sub 1 equals 0, a sub 2 equals 1, and a sub n, so any term I want to find, is the term that's 2 before it, plus the term that's 1 before it. And this is only true when n is greater than or equal to 3, okay? Meaning the first 2 terms we have to have, and after that, then we can start to use this pattern, okay? So this right here, all 3 lines, those are all together our recursive formula, okay? So we want to make sure that we know all of this is the recursive formula. All right, and the way we got it, we found the pattern from looking at the number, okay? Now, I think I mentioned earlier that the recursive formula tends to be a little easier to find because we can look at the numbers and kind of see what the sequence, what the pattern is, okay? Now, the explicit formula for this one is actually pretty tricky, and I'm not going to make us find it, but rather I'm going to give it to us, okay? Just to kind of drive home a point that sometimes that recursive formula is actually a little bit easier, and finding the explicit one can be a little bit more challenging, okay? But once I give you this formula, let's talk about the different uses of a recursive versus an explicit formula, right? What are the benefits? What are the drawbacks? So it turns out that for this sequence, okay, and some of us might even know that this is the Fibonacci sequence, okay. But in this particular sequence, the explicit formula is as follows. The really long fraction bar. In the numerator, we have 1 plus square root of 5 over 2 to the power of n minus 1 minus the square root of 5 over 2 to the power of n, all over the square root of 5. Okay? So, the gross formula. Why would we ever want an explicit formula if we could find the recursive one just from the pattern? Like, why do we need two different kinds of formulas? So, let me tell you why. This recursive formula is handy. It's handy because you can usually find it from the pattern that's happening in the numbers. But in order to find any term, you have to know the two terms that come directly before it, okay? Meaning, if I wanted to find, say, a sub 100, the 100th term, I would need to know, all right, we need the two terms that come before it, a sub 98 and a sub 99. All right, so the only way to use this recursive formula, if I wanted to find a sub 100, I need the 98th term and I need the 99th term. Well, I could probably sit and write out all those terms, but what happens if I wanted to find the 1000th term? Now I need the 998th term and the 999th term. And in order to find those, the only way to do it is brute force. I have to find every single term. That seems like a lot of work, okay? So, easier to write the recursive formula, but sometimes not as beneficial. What about this explicit formula? To find a sub 100, we just plug n equals 100 into the equation, okay? So even though this equation is grosser, if I wanted to find the 100th term, I just plug in 100 for n, figure out the number, we're done, okay? So beneficial because it's easier to find a specific term, but a little bit harder sometimes to get to that explicit formula. All right, so let's get this all on one page for us here, all right? But in the next few videos, we're going to practice some finding explicit formulas, finding recursive formulas, and actually working with them to find the specific term, okay? So come on back for a little bit more practice.